In this video, we will look at steady-state analysis of a system. So we will not set up the dynamic equations for the system, but we will instead solve it in a steady-state situation. So we'll not look at the pressure gradient and so on. We'll look at a situation where our system has settled at some constant velocity, some constant pressure levels in the system. The system that we will look at is the one shown here, where we have a differential cylinder that is connected to a directional valve, which again is connected to a pump that is connected to a pressure relief valve. We see here in the picture that the pump is a variable displacement pump. We will now see that the pump is set to full displacement all the time, and then try to see what is the steady-state solution for the system. The first thing that we do is that we set up these symbols for the system. So we define the flow direction and we give them a name. We define pressure knots, where we have this 4 and we have 1 over here, and then 2 and 3 in the 2 cylinder chambers. So that is actually our control volumes. In each of those control volumes we assume the pressure to be constant all over. That means that we don't model the pressure drop in the hoses in this situation here. And with this defined, we can start setting up the equation. But let's just move our figure. So what we do now is that we solve the system from the pump all the way through the system and back to the tank for the flow. So first we could look at what is the continuity equation for this pressure knot 1. And when we define the continuity equation for a steady system, we would like to have a continuity equation that is flow in minus flow out equal to volume change. So we don't include the last part with the pressure gradient. And doing that for our knot 1, the flow into that will be the pump flow. Flow out will be Q1 and Q2. And the volume change will be 0, as we assume that the pipes or hoses is not deflecting, at least not when we are in steady state. Q1 is the flow across the relief valve, Q2 is the flow into or through our directional valve. So now we'll model the system where we have the directional valve in the setting where it is supplying flow from the pump until chamber 2. So we assume it to be in the picture that we have shown over here. So that is moved into the middle so that we have a flow into the piston side and out from the rod side. So now let's look at control volume 2, which is the piston side of the chamber. The flow in and the flow out, and then the volume change. So the volume change is the velocity times the piston side area. And if we now calculate from the pump side on, we can rearrange this such that we have that Q2 is equal to the pump flow, which is equal to the displacement of the pump multiplied with the rotational velocity of the pump. And plugging that in, you will get 50 liters per minute. And now down here we know the Q2, so we can isolate for the piston velocity. And plugging in the numbers, we'll reach this piston velocity. And now to the rod side chamber that we have up here, which is our control volume 3. And the flow in will be 0. We will have a flow out Q3, which is from this pressure knot 3 through the valve to the knot 4. And now we have the volume change with the negative sign, because the volume is getting smaller when we have a positive cylinder velocity. So Q3. In the note you can see how I include the units when calculating from rotational velocity to flow in liters per minute and from displacement in cubic centimeters and so on, in a very straightforward way, so that I know that I get the right unit all the time. And now the final flow that we could define is out of the pressure knot 4. So now we have the flow through the system. We start at the pump, go up through the valve to the cylinder, back through the cylinder. Interesting to see is that the flow into the cylinder and out of the cylinder is not the same. And the ratio between these two flows, well, hopefully they are equal to the cylinder area ratio. So now we have all the flows for the system, and we can see that we start with the flow, because what we know for this system is that the pump has some given displacement. We set that to fixed, a maximum of 25 cubic centimeters per revolution. We have a rotational velocity that is also given, and then we know what is the flow out of the pump. We can't calculate the pressure because the pump is a flow source, you could say, so it gives out some flow, and then depending on what is after the pump, we have some given pressure. So let's have a look at the pressure. And the pressure that we know is the tank pressure. We know that is 1 bar. And then from there on we can see that, okay, the flow Q3, that could be described with an orifice equation. And if we have the area from our B to T, here instead of T, I should maybe have used the 4 instead, so we can write 4, but because we don't include losses in the hoses, the pressure 4 will be equal to the pressure T. So this equation we can set up for the flow through the valve from B to T, and we already know that flow. So now we can isolate for the pressure 3. Yeah, you're right. I know that the square root and the to the power of 2 cancels out. It's just to show the full picture of what we're doing. So we see that the pressure P3 in the rod side chamber is equal to the pressure P4 after the valve, plus some pressure difference across this valve. So in the tank we have 1 bar, that's the same as 10 to the power 5 Pascal, and we have the pressure loss here in Pascal. So we see that our P3, and instead of writing the plus, we switch this with the 8. So now we have P3, and that's the pressure in the rod side of the cylinder. So now we need an equation to calculate what is P2. And the equation that we can set up is Newton's second law. And as we're calculating for steady state, we have 0 acceleration. Therefore we can write that the mass times 0 is equal to, and for this system we assume the efficiency to be 1, so we have no losses in the cylinder and we have no losses in the pump. And we already know the P3, so now we want to find P2. And let's just, for the fun of it, try and split this up in the two terms. And this last term is actually what is requested to lift the mass that we are moving. This first term is a term we need to overcome the back pressure that we have just calculated up here. So you can say this is something that work we get out if we calculate this together with a velocity. The top part here, the force times velocity, is the power that we get out. But if you plug in the numbers here, you'll see that we get 160.19 bar. And that's now the pressure P2. So now we only need the pressure P1 just after the pump. And we want to do that in the same way as we did with finding the pressure 3. So we will need to find the pressure drop across the inlet from 1 to 2. So now I've set up the equation for the pressure drop. And this pressure drop is a bit similar like the pressure drop that we calculated up here, right? The area in the valve is the same for the in and the outlet. So that is the same for it. So this pressure drop, will that be the same as the pressure drop that we found up here, the approximately 7 bar? Or would it be lower than these 7.3 bar or higher than these 7.3 bar? It should be higher, right? Because the flow that we have in is the 50 liters and the flow that we have out is the 30 liters. The discharge coefficient, the area and the density is the same. So therefore this pressure drop is somewhat higher on the other side. It is 19.67 bar, leaving us with a pump pressure of approximately 181 bar for this system. And now we have all the flows in the system, Q2 and Q3, and Q4 is the same as Q3 if we assumed, what is it that we started by doing without even mentioning it? Well, we started by assuming something about the pressure relief valve that we have in here. We assumed that that is closed. So before I could calculate all of this, in this equation here, I set that to 0. And that is my guess. So I'm guessing that Q1 is 0. And when will Q1 be 0? Well, Q1 will be 0 when the pressure relief valve that we have up here sees a pressure in the point here that is lower than the cracking pressure for the pressure relief valve. So the 180 bar has to be lower than what it is for this exercise. So the exercise set the pressure relief valve to be 250 bar, and therefore this is lower, so this calculation is good, and the guess that we had up here was okay.